And thank you all for coming. I'm delighted to share some of what we have learned from the Messenger mission to Mercury and to address the question in front of you: how and why is Mercury different from its sibling rocky planets? Of course, Mercury is one of the four inner planets in our solar system, the so-called rocky planets. And that in itself is a reason for studying one of Earth's nearest neighbors. But the four planets themselves are outcomes of experiments, an experiment in how a rocky planet is formed and evolves. The experiments had four very different outcomes, and so our ability to generalize our understanding of how to make planets like ours and rocky planets around other stars demands that we at least explore the range of outcomes amenable to exploration by spacecraft and in situ study. Moreover, Mercury is an example of a particularly dense planet, and it was interesting that a month ago, astronomers led by Grimm and colleagues announced the discovery of extrasolar planet K2-229b, which might have a density, despite being much larger than Mercury, that is similar to that of Mercury. And you see it compared with other large rocky exoplanets that have been much in the news, that have Earth or Venus-like masses and radii and mean densities. But K2-229b is denser than those, and despite being 2.5 Earth masses, might have Mercury-like density. And so one could argue that a better understanding of our own high-density rocky planet informs us about the formation of metal-rich rocky exoplanets. The study of Mercury by spacecraft has a fairly limited history, and that's very much in contrast to the exploration of much of the rest of the solar system. And Mercury's only been visited by 2 spacecraft, and one of them was more than 40 years ago, when Mariner 10, the last in the Mariner series, a backup you can still see today near the Dulles airport, was the first spacecraft to visit Mercury. And it did so 3 times as it flew around the sun, encountering Mercury on an interval of about 6 months, which happened to be Mercury's solar day. Mariner 10 discovered that Mercury has its own internal magnetic field, like the Earth, like the giant planets, unlike Mars and Venus. We think Mars once had a magnetic field and lost it very early in its history, and we have no evidence as to whether Venus had a magnetic field. But tiny Mercury, 5% of an Earth mass, still has a magnetic field today, and it's Earth-like in its geometry, although the 3 flybys of Mariner 10 did not define that field very well. Mariner 10 carried a camera system and imaged a little less than half the planet on the 3 flybys, and showed a planet to be heavily cratered, superficially resembling Earth's moon and having a density of impact craters much like that of the lunar highlands. It also had smooth areas of plains that, were they on the moon and were they dark, like the lunar maria, would be inferred to be volcanic, made out of material that erupted as molten rock and flowed as a low viscosity liquid. But on Mercury, the plains are not dark as they are on the moon, and so that led to decades of debate as to whether the plains are volcanic on Mercury. After the Mariner 10 mission, Earth-based astronomers made some other intriguing discoveries about Mercury that whetted the appetites of the planetary community. Here you see an image of the sodium emission from sunlight scattering on the day side of Mercury. In 1985, 86, astronomers discovered sodium and potassium in Mercury's atmosphere. And in 2000, they announced the discovery of calcium. Those 3 species are easy to see because of a phenomenon known as resonant emission scattering. The abundance of the species in the atmosphere is so much larger than the flux of these atoms from the solar wind that they must be derived from the rocky material of the surface. Ground-based astronomers using radar also announced in 1992 the discovery of radar bright deposits at the poles of Mercury. These were thought to be located in the floors of impact craters in areas of permanent shadow. The shadow is permanent because Mercury's spin axis is almost perfectly normal to the orbital plane of the planet. That is to say, the obliquity is nearly 0 degrees. It's 2 minutes of arc. And so an impact crater or a hole in the ground surrounded by a mountainous ring at high latitudes has large areas in permanent shadow where because of the low density of the atmosphere, the surface temperature is exceedingly cold. The surface looks out into black space, and the low temperatures are sufficiently low as to preserve water ice for geologically long periods of time. So the characteristics of the radar signal, the high backscatter, the depolarization of a polarized radar signal sent out from the Earth, and the temperature models developed from models of impact craters at high latitudes on Mercury led to the proposal that these deposits are water ice. So that was an intriguing idea that demanded testing by spacecraft. So in the late 1990s, a group of planetary scientists proposed to NASA a mission to Mercury as part of a program where mission concepts were competed. Most of the fields of space science have these small missions that allow these competitions where NASA doesn't direct a particular target or type of mission, but allows good ideas to come forward. And then they apply a good deal of scrutiny to test the technical feasibility of the idea. And in 1999, they selected our mission to go to Mercury for only the second time, but to go into orbit and to take a class of instruments that were 3 decades beyond those of Mariner 10 and allowed us to make measurements that couldn't be done in the 1970s. So I want to talk about 3 broad areas where Messenger made discoveries, having gone into orbit about 6.5 years after launch, after having flown by the Earth once and Venus twice, and Mercury itself 3 times before orbit insertion in 2011. We were originally approved for 1 year in orbit, but things stayed healthy, and we got 2 additional extensions and ended up with a little over 4 years of orbital observations of one of our nearest neighbors. So I want to talk about what is Mercury made out of, because we took geochemical remote sensing instruments to Mercury for the first time. I want to talk about what we could learn about Mercury's internal magnetic field once we were close and in orbit, that had been discovered by Mariner 10 but hadn't been mapped out in any detail. And I want to talk about what geochemical remote sensing and geophysical remote sensing told us about these polar deposits discovered in the early 90s by radar astronomers. So the surface composition. The one thing we've known about Mercury for about 70 years is that it is very dense, like the extrasolar planet that I mentioned was announced a month ago. The density of Mercury, considering its small size, can be met only by having a large fraction of iron. Iron is the only element in the sun or in meteorites of sufficient abundance and density to match the mean density of Mercury, so that unlike Earth and Venus, which have a central metallic core that occupies about 30% of the mass of the planet, on Mercury the core must occupy 60 or 70% of the mass of the planet. And the rocky fraction is very, very small. A thin shell, about 400 kilometers thick, no more, over this essentially metal world. Now, for many years, we've had ideas for how to make a planet with a much higher fraction of metal than silicate, a much higher fraction of metal than rocky material. And most of those proposals, and there were many for Mercury in particular, have invoked high temperature processes. Maybe Mercury assembled only from materials that condensed at the highest temperatures near the host star before a nebula of gas and dust was dissipated by solar winds. Maybe Mercury formed as a planet similar in composition to the other rocky planets while there was still a hot nebula. And that hot nebula vaporized the outer silicate fraction, leaving behind an interior metal core preferentially. Maybe Mercury formed a differentiated planet with a composition much like the other inner planets, and there was a giant impact, a collision with an object nearly the size of Mercury that so disrupted the planet that most of the rocky fraction was lost and not reaccreted. So all of those ideas invoke some very energetic process that would have subjected Mercury to a high temperature phase. And so a prediction of all of those ideas before we ever got to make measurements was Mercury should be depleted in elements that are removed by high temperatures, so-called volatile elements. Along the way, we got some high-resolution imaging. We resolved the question of the importance of volcanism. 28% of Mercury, shown in garish purple, it consists of these smooth plains that we now recognize as volcanic, younger than the most heavily cratered terrain on the planet. And in some areas, as perhaps you can see in the lower right, there's evidence for modification of landforms by a rapidly flowing liquid that creates channels that leaves behind islands. And if we saw such a channel on Mars, we would guess that it was formed by running water. We don't think that on Mercury, but it could have easily been formed by a high temperature, low viscosity, high eruption rate magma, volcanic eruption. And in the case of this particular channel, it leads down into one of the smooth plains that fills a nearby topographic low, an impact feature. So our extent to recognize there are volcanic features everywhere on the planet, we suspect that most of the surface of the planet that we can see today, even the heavily cratered terrain, was once emplaced volcanically. So whereas we once had a question, how important was volcanism on Mercury, now it is recognized that the crust that we can see was probably all emplaced volcanically. We've made measurements of the elemental composition of the surface using two kinds of geochemical remote sensing. And you see plots of element ratios here, two different pairs of element ratios. And all of these measurements came from a technique that makes use of X-rays. The sun gives off X-rays because Mercury doesn't have an atmosphere to speak of. The X-rays make it all the way down to the surface, and the atoms at the surface absorb the solar X-rays and fluoresce at an X-ray wavelength that is diagnostic of the atomic species. So from different energy intervals for X-rays, we can determine the abundance of major rock-forming elements like magnesium, aluminum, calcium, silicon. What this plot shows is that, I forgot, we don't have a pointer except for this. What this plot shows is that the lunar highlands and most of the lunar volcanic rocks fall in a different part of the plot than the red symbols for Mercury. The most common rock on Earth are the volcanic rocks of the seafloor, making up 70% of the surface of the Earth. They look different from what we see on Mercury. And in fact, Mercury has a major element composition that is different from the surface of any other solar system object. That composition varies regionally. There are variations as a function of age. There are variations that we don't understand, a so-called high magnesium province. And it's fuel for more research on what we're seeing in terms of the origin of these variations. But there's some indication that the volcanic materials that were produced on Mercury did, on average, vary in composition over time, probably sensitive to cooling of the planet early in its geological history, and superposed on that are other geological processes that we're still unraveling. Another geochemical remote sensing method makes use of gamma rays that are produced by the interaction of extremely energetic particles known as cosmic rays with the materials at Mercury's surface. And these gamma rays can themselves, because of interactions with with atoms in the near surface, be diagnostic of elemental species in surface materials. And an important metric for Mercury was how much iron we see. Remember, we think Mercury is mostly iron. It's 60 to 70% iron by mass. But at the surface, there's very little iron, less than 2% by weight. And virtually none of that iron is in the silicate phase. And that's very much in contrast with what we see on the Earth, Moon, Mars, or Venus, where there's a lot of iron in the rocky fraction, as well as in a metallic core. And what that speaks to is that the chemical conditions known as chemical reduction or oxidation were different on Mercury than they were for the precursor materials of the other major planets. And we would say that the material out of which Mercury was assembled is much more chemically reduced than the material that contributed to the formation of Earth or Venus or Mars or even the Moon. Another surprise was that Mercury is very abundant in the species sulfur. Sulfur is normally thought to be one of those elements that's reasonably volatile, is removed by high temperature processes. But its abundance on the surface of Mercury is a factor of 10 bigger than the abundance on the surface of Earth. And this plot just compares it with another elemental ratio to show that there's some correlation and probably telling us something about where the sulfur resides, what minerals on the surface of Mercury. But the absolute abundances of sulfur, several weight percent, were surprising and weren't predicted by any of the models for how Mercury got assembled. Another metric that the geochemists use for the history of a planet and particularly the extent to which volatile materials are retained is this ratio of potassium to thorium. These are elements that we can see with a gamma ray spectrometer because they have isotopes that are naturally radioactive. They have some geochemical affinity in terms of processes that go on inside the planet, but potassium is much more volatile than thorium, which is not volatile. And the ratio of potassium to thorium is much lower for a body like the Moon, which has lost volatiles, than it is for the larger planets like Earth or Venus, we think, on the basis of some Soviet measurements on the surface, or Mars, which is in gray and takes up these symbols here and these meteorites. So the expectation was that Mercury on this kind of plot would be depleted like the Moon, and volatile elements would have a potassium-thorium ratio well off the line for the big planets, but it does not. The red area is from Mercury, and it's on the same line as the other major planets. Another element that is easily removed by high temperatures is chlorine, a halogen. And here you see a range of magnitudes for a variety of meteorite types, some Mars samples in red, some terrestrial samples in green. And this is showing chlorine as a ratio to potassium as a way to calibrate what's being measured. But the abundances for Mercury are as high as they are for Mars, which is thought to be a volatile rich planet. They're higher than they are for the Earth. They're higher than they are for many meteorite classes. So an element easily removed by high temperatures, chlorine, is very abundant on Mercury, contrary to the predictions of the models before we got there. One last independent argument is that imaging from Messenger, when we got into orbit and were able to take high-resolution images of the surface much better than Mariner 10 was able to do, showed a terrain type that we hadn't expected. Notice the scale bar. These are hundreds of meters across. depressions, irregular in plan form, no raised rim, so they're not impact craters. They're often very bright, or they have halos of bright material. They got named hollows because we didn't have any other name for them. They tend to be inside or associated with deposits in impact craters. And they do not have any impact craters superposed on them, which is to say, on geological timescales for a body like Mercury, they're some of the youngest features on the surface. And the hypothesis is that they are the product of recent or ongoing removal of material. And that material is the loss of something that is volatile on at Mercury surface conditions that has been exposed to the surface fairly recently by an impact feature that has excavated material from depth and brought it to Mercury surface conditions where the loss begins. So this is a geological argument that there is volatile material at depth. We don't know the identity of the volatile material. There's some ideas, but it's not merely volatile material at the surface. There's one more story that came out late in the Messenger mission when the spacecraft was getting closer and closer to the planetary surface, and that has to do with regions that were called low-reflectance material. What you see on the left are three areas that have been imaged in color, and the color has been stretched to emphasize differences in spectra. What you see on the right are the spectra, reflectance versus wavelength for these three low reflectance material, and by comparison, average material for Mercury and some brighter high reflectance red planes. And here they are relative to the brightest material. And you see that they are higher in reflectance at short wavelengths, which the spectroscopists say means they're relatively blue. And so they end up blue when one does this enhanced color imaging. And the question is, what is this material? What makes them dark? And you see that spectrally, they're not very different in the shape of the reflectance spectrum, only in the absolute level. And so whatever darkens them doesn't change the shape very much. It's spectrally neutral, but it changes the overall reflectance by a great deal. And the geochemists who've looked at these kinds of questions in greatest detail postulated that the common elements that could have accounted for this change in reflectance and no change in shape are primarily elemental materials. Very low, small grains of iron could do that, and so could carbon in the form of graphite. Both of those materials are very dark and spectrally neutral. As we got closer and closer to the surface, another instrument on Mercury on Messenger was brought into play, and that was the neutron spectrometer. Remember I talked about the cosmic rays interacting with the surface materials on Mercury. One of the products of the collision of the cosmic rays with atoms near the surface of Mercury is a cloud of neutrons that have a range of energies. And in the lowest energy range, the different elements at the surface of Mercury have a different ability to absorb more or less those neutrons and change their spectra as a function of energy. And in particular, if the dark material on Mercury were dark because it had more iron, one should see a lower flux of thermal neutrons. And if the dark material on Mercury were dark because it had carbon, one should see a higher flux of thermal neutrons. And you see some of the experiments that were done late in the mission when we're flying over the low reflectance material, and the field of view of the neutron spectrometer was filled by these small areas of low reflectance material that in all cases, even though one has to invoke statistics, the low reflectance material was higher in thermal neutrons, meaning that's a vote for carbon over iron as the cause of the darkening on Mercury in the low reflectance material. So carbon in the form of graphite is abundant on Mercury at the level of about 1% on average, and several percent, 4 or 5, in the low reflectance material. And one of the things that's interesting about that finding is that there was a prediction made from experimental petrology that graphite might be abundant on the surface of Mercury, and it's illustrated in this cartoon. We think that the crust of Earth's moon is the result of an early phase of the moon's history when, I'm having some gravitational interactions with chalk. The early phase of the moon's history involved a time when the outer part was completely molten, a so-called magma ocean. And as that magma ocean cooled on the moon, because the average composition of the moon imparted a density to the magma that was fairly high because of the abundances of iron and titanium, one of the common elements that crystallizes out of that magma, known as the feldspar that has calcium and aluminum, is actually lower in density when it crystallizes than the magma around it. It floats, and the hypothesis is that it formed the lunar crust that we see today in the bright areas of the moon. On Mercury, the rocky fraction is so low in iron and titanium that even if the same mineral were to crystallize in a cooling magma ocean, it would not float, it would sink. The magma would still be less dense. And in fact, the prediction of these workers was that the only mineral crystallizing out of a magma at Mercury, if there was sufficient carbon in the magma ocean, would be graphite. And so the cooling of a magma ocean on Mercury could lead to concentration of carbon, whatever it started with, in a near-surface graphite layer. And that would be near the surface even today, even if it were overprinted by billions of years of volcanic eruptions, it would still be concentrated near the surface, where it can be excavated by impact craters and brought to the surface as low-reflectance material. So this prediction matches what was seen with the neutron spectrometry and the reflectance spectrometry. So it was a nice confirmation of a prediction of a magma ocean model for Mercury, and a statement that whatever material that was aggregated to form Mercury had to be fairly carbon rich. So we ended up with some surprising inferences about how Mercury formed compared to what we expected before the mission got to Mercury, in that the abundances of moderately volatile elements like sulfur and potassium and sodium and chlorine were much higher than any of the models predicted. Models like bathing a fully formed Mercury in a dense and high temperature nebula, or impacting Mercury with an object nearly its same mass and disrupting the outer silicate shell, ejecting it, not only from Mercury's gravitational field, but from Mercury's orbital zone around the sun. That both of those ideas predicted abundances of these elements far lower than what we saw. And so at their most straightforward form, they are rejectable. And we're left with the problem that we don't have a fully formed theory yet that is complete in its physics and its chemistry for how to make Mercury. One has to do it from chemically reduced precursor materials. One has to do it with comparatively volatile rich materials so that the volatiles are retained. One has to end up with a planet that is 60 to 70% metal by mass at the end, and with a composition that matches what we see at the surface today, including the high carbon. So my colleagues who work on these kinds of things are hard at work, but the jury's still out. Let me turn to the magnetic field for a few minutes. Remember that Mercury is the only inner planet other than Earth to have a modern global magnetic field. The Earth's magnetic field is dominantly the field of a dipole, a bar magnet at the center of the planet. It is continually renewed by convective motions in Earth's fluid metallic core through a process known as a dynamo. Stars have dynamos and magnetic fields. Planets have dynamos and magnetic fields. And Earth-like planets have their dynamos in a fluid metallic core. Messenger was in a very eccentric orbit. We did that for thermal reasons. We did that for energetic reasons. We did it because we couldn't survive successive dayside passages at low elevation in a circular orbit. But it meant that on every orbit we passed through all of the major boundaries of Mercury's magnetosphere, which were Earth-like, bow shock, magnetopause, plasma sheet, but miniaturized. Miniaturized because the magnetic field of Mercury is much smaller than that of the Earth, a factor of 1,000 in dipole moment, and because Mercury is much closer to the Earth, where the solar wind is that much stronger. So the interactions are much stronger. And the miniature magnetosphere means that all of the things that happen on Earth's magnetosphere tend to happen at Mercury's magnetosphere, but they're amplified. The extreme phenomena like magnetic reconnection occur much more frequently. And the dynamics of the magnetosphere, including wave propagation and plasma transport, happen on much shorter timescales because of the smaller size. So it's an interesting laboratory for studying an Earth-like magnetosphere. But we were interested primarily in what the magnetic field of Mercury looks like. And we had this surprise. Remember, we were in this eccentric orbit, so the analysis was a little unconventional. But what we showed is that the magnetic field of Mercury, unlike that of Earth, unlike that of the rest of the planets that have magnetic fields, is not at the center of the planet. It's offset. It's offset to the north of the planet along the rotation axis by about 20% of the planet radius. And here you see the evidence for this. Every time we went around the planet, we could determine the location of the magnetic equator, which is the place where the magnetic field is parallel to the spin axis. And if you plot those locations on each orbit as a function of the fixed longitude on the planetary body, you get a plot like this. It's offset from 0, which is the geographic equator. It has some small oscillations, some of which constrain the tilt of the dipole, but it's constrained to be very, very small. So this is the magnetic field of a dipole, like that of the Earth, but not at the center, offset by 20% of Earth's radius for reasons we still don't understand. But what this means is that the magnetic field of Mercury is very asymmetric about the equator. The field at the north polar region is bigger than the field at the south polar region by a factor of 3. The area of magnetic flux that is open to the solar wind and to the heliosphere is much larger in the south than it is in the north. And these magnetic field lines that are open are also highways for energetic particles from the sun to stream down to the surface of Mercury, where they can interact with the surface, change the local chemistry, generate atoms that contribute to Mercury's atmosphere. So how long this asymmetry has persisted, are there timescales for the asymmetry reversing? We don't know. There were actually no models for planetary magnetic fields prior to the MESSENGER mission that predicted offset dipoles of this magnitude. There are now some, but I'm not sure we have the right one yet. Late in the mission, the MESSENGER spacecraft got closer and closer to the surface of Mercury prior eventually to crashing on the surface, which constituted the end of the mission. But when we got close enough, we could begin to see the signal of something else. Now, on Mars and on the Moon and on the Earth, the rocks of the crust are magnetized. They have a permanent magnetization. In most cases, they acquired that magnetization by cooling in the presence of a magnetic field, and then having minerals that whose grains could acquire this permanent magnetization when the temperature dropped below a certain level. We didn't know whether that was the case on Mercury, but we were eager to see whether we could find any evidence for crustal magnetic fields. So as we got closer to the surface and we made measurements of the magnetic field like this, we could take out all of the contributions from the dipole, all of the contributions from the current systems in the magnetosphere, and look at what was left. And here's one particular orbit, and what's left has this kind of shape. It's much smaller than the total field measured, but it has a distinct shape. And lo and behold, when we did the next orbit, we found that the shape was very similar. So it wasn't a random residual. It had some coherence from one orbit to the next, and we could map these areas of magnetic high and low and put them on a geological, or in this case, a topographic map. And areas are positively or negatively magnetized over distances of hundreds of kilometers. And so this was helpful evidence that we're not seeing the internal magnetic field down to the core, we're seeing something much more local. And we did some tests of that hypothesis by flying over some areas at different altitudes, at different phases in the mission. So here are 3 passes over essentially the same terrain, one at 120 kilometers altitude, one at 80, and one at 35. And you see that the magnetic anomalies get much larger as you go closer to the planet. And that tells you that you're getting closer to the source of the magnetic anomalies, and in particular, that the sources must be very shallow in the crust. So that means that Mercury has crustal materials that can acquire permanent magnetization. The fact that some of these anomalies correlate with geological units that we can date approximately by the density of impact craters to be almost 4 billion years old means that Mercury had a global magnetic field early in its history, and it has one today. So that's very Earth-like for a tiny planet like Mercury, and we're still wrestling with the implications for what that means about the interior cooling and about magnetic field generation in Earth-like planets. Let me end with the topic of polar deposits. You remember this plot. It was an image taken at the Arecibo telescope of the North Polar region of Mercury. And the bright areas, which happen to be colored yellow, it means nothing at radar wavelengths, are the areas of the so-called polar deposits. And Messenger carried a number of instruments, particularly to look at this hypothesis that we're looking at water ice. The imaging system itself, the neutron spectrometer, because hydrogen is one of the best absorbers of neutrons, and so a neutron spectrometer is very sensitive to hydrogen-rich compounds like water, and a laser altimeter. So what did we find? First off, the imaging told us early in the orbital phase of the mission, when we had lots of measurements of the South Polar region, because we were high above the planet, we could measure what fraction of time in a solar day each area of the surface was illuminated by sunlight. And you see that fraction here. Black is 0, orange is a lot. You see that we're looking at a polar projection, South Pole in the middle. We go out to 73 degrees south at the outer circle. So there's a variation with longitude that has to do with Mercury's spin-orbit resonance that I can explain if somebody's interested in. But what's important for the next few slides is that the areas in black get 0 sunlight. They're in permanent shadow. And Mercury is in a very stable orbit where its orientation is fixed in space as a result of the resonance that it occupies between the spin and the rotation revolution period around the sun. And so in one solar day, an area that is permanent shadow is also in permanent shadow for 1 billion years. And it means these are candidates for places that are very cold. So if one overlays the radar bright deposits in the South Polar region with the areas of permanent shadow, there's a very good correlation. You see the conclusion here. All radar bright features reside in structures that have permanent shadowed areas on their floors. So that part of the hypothesis was confirmed early in the Messenger mission. Remember that the Messenger spacecraft was close to the planet in the northern hemisphere, and so a lot of the focus was on the North Polar region, and that's where the neutron spectrometer had information. And what you see here is a comparison of the observations of the neutron spectrometer at intermediate energy, for intermediate energy neutrons versus 2 models for the composition of the polar deposits. So this is a plot of the integrated flux of these epithermal neutrons as a function of latitude from 30 north to the North Pole. And the dotted line is the prediction if the polar deposits have no hydrogen. There shouldn't be any relation with latitude. If the polar deposits are 100% H2O, water equivalent hydrogen, WEH, then the blue line pertains. And you see that the red observations follow the blue line. This is if all of the deposits known on the basis of radar imaging are pure water ice. You get the blue line, and that's matched for epithermal neutrons by the red curve. The neutron spectrometer was also sensitive to higher energy neutrons, which are more easily absorbed by near-surface material. They're also less abundant, so the error bars are larger. But the black shows the case if the polar deposits don't consist of any hydrogen, the blue if it's 100% water equivalent hydrogen, and the red, the observations of these higher energy fast neutrons. And what you see as you get close to the pole, even with the large error bars, is that you're splitting the difference between no water ice and 100% water ice. So to match these data, as well as the data from the previous plot, there's a single model that works, and that is one where the deposits are mostly water ice, but they are not exposed at the surface. They're covered by an insulating layer a few tens of centimeters thick. That insulating layer is sensitive to the highest energy neutrons and absorbs them enough to account for this difference, but it doesn't do that with the slower neutrons. So what is that insulating layer? This is a plot of reflectance of the surface at the wavelength of our laser altimeter. The laser altimeter was on board to measure topography, and it used a near-infrared laser wavelength of 1064 nanometers. And there's a color bar over here, and it shows that most of the area near the North Pole, which is at the center, and this gray area says that our orbit wasn't strictly polar, but was inclined by this much from the pole for scientific reasons that are not relevant to this argument. But on average, the reflectance are these yellow-green colors, like here. So the reflectance at this wavelength of most of Mercury in the North Polar region is like the rest of the planet and has this value, 0.17. But in a number of impact craters, and you can see them here as just dark spots, the reflectance is less by a factor of 2. These are nadir pointing measurements, and this reflectance is in fact lower than any other surface on Mercury. And these craters are also ones that host polar deposits on the basis of Earth-based radar. So given that they are impact craters, that they are topographic depressions surrounded by a mountainous ring, and that they have areas of permanent shadow, the measured topography can be used to make thermal models of the surface temperature and the near surface temperature given solar insolation. And the thermal models predict that in these areas that are very, very dark, water ice would be stable if buried by an insulating layer a few tens of centimeters thick, but would not be stable at the surface. Not be stable unless you're closer to the pole than any of these measurements here. So later in the mission, we were able to take images of the interiors of some of these polar craters. What we did was take very long exposures. We washed out the areas in sunlight and focused on the areas that were in permanent shadow to see what we could see. And I'm going to show you results from just 2 craters. A small crater called Fuller, that's well off the North Pole, which is up here somewhere, and a much larger crater much closer to the pole called Prokofiev, 112 kilometers across. For Fuller, we could use nadir pointing measurements. You took an image, a normal image, you would see something like this. The outline of the crater is in pink, and you have to really stretch the imaging system and overexpose the areas outside the crater to look inside, and this is what you see. You see that the permanently shadowed region does have features that you can image, and the in particular. There's this dark unit here that shows up easier if you look at it with arrows pointing at it. That region corresponds to the radar bright material mapped from Earth, but it's dark. It's darker than anything we see elsewhere on Mercury, even at visible wavelengths. And the opposite is true for Prokofiev, much closer to the poles, not viewed with nadir observations, but viewed off nadir. A big enough crater that only part of it is in permanent shadow, this part to the southeast. That is the part that has the polar deposits as seen by Earth-based radar, showing here in yellow. And what the infrared wavelength laser altimeter showed is high reflectivity, much higher than anywhere else in this part of the polar deposits. We didn't have complete sampling, but where that radar bright polar deposit was sampled, the reflectance was a factor of 3 or 4 greater than the average for the planet. So if you put all this together, you get this image at visible wavelengths of the interior of Prokofiev. I point your eyes to this area here of slightly brighter interior material and put that in context and compare it with the location of the radar bright material. And so this is an area where the radar bright material does have a visible signature in the interior of the crater, but the visible signature is high brightness relative to surroundings rather than low. So if you put all that together, we came up with this simple scenario. The scenario is that the polar deposits are mostly water ice. They have to be mostly water ice to fit the neutron spectrometry. But there's something else, and that something else is the dark material that covers the polar deposits in most of the regions off the North Pole. So what is that dark material? Well, here's the idea. The idea is that most likely water on a planet like Mercury is delivered from impacts of comets, impacts of volatile rich asteroids. And these comets and asteroids can hit anywhere on the planet, but some of, and are volatilized on impact, but some of the molecular H2O is trapped in Mercury's gravitational field and finds its way to the coal traps at these very high latitudes. Now, it's got some dark material with it, a kind of dirty snowball idea going back to Whipple, where there's dark material as well as water ice. And if that dark material is something that is stable to somewhat higher temperatures than the water ice, then it will get concentrated at the surface in these areas where there's a little bit of sunlight, either direct or reflected off the walls. It'll get concentrated because the water ice will be preferentially lost at temperatures where the water ice is not stable on geological timescales, but the dark material is. Now, we don't see this dark material outside of the areas of permanent shadow, so it too must be a volatile. It is lost at high temperatures. It can't survive direct sunlight, but it is stable to higher temperatures than the water ice. And it's the surface covering of these polar deposits on all these craters off the poles. So what is it? We don't have any chemical information. We have its reflectance. We have something about its temperature limits of stability. And we have, by hypothesis only, that it is associated, including its delivery mechanism, with the water ice. And so on the basis of observations of comets, on the basis of observations of volatile-rich meteorites, on the basis of observations of the material that coats the surfaces of small objects in the outer solar system, the leading hypothesis is that this dark material consists of organic compounds. The organic compounds are common in comets. They're common in volatile-rich meteorites. They have the reflectance, and if we had more measurements, they have a diagnostic spectra, red spectra, that is common throughout the outer solar system. They would be delivered to Mercury by the same impacts that we think delivered the water ice. And there's one more clue, although I don't have a plot of it. There are thermal models of the surfaces of some of these dark layers that cover polar deposits in impact craters that have enough resolution to see variations in temperature across the surface of the deposits. And the reflectance, the darkness of the deposits correlates with the temperature from the thermal models. And that correlation is interpreted to mean that the organic compounds consist of a mix of compounds of slightly different volatility and different, reflectance, accounting for that correlation between temperature and what we can see with our imaging system. So let me close and open for questions with this last slide. That I didn't cover everything we learned about Mercury, but three major topics that really changed our view of one of our planetary neighbors, and by implication, broadened our understanding of potential outcomes and formation processes of rocky planets in our solar system and solar systems like ours. We must come up, and haven't yet, with a model for planet formation for Mercury that yields not only a high fraction of metal to silicate and the high mean density, as we're starting to see for bodies around other stars, but in the case of Mercury, a high abundance of volatile compounds, sulfur, potassium, sodium, chlorine. So we're retooling our planet formation models to incorporate chemistry and temperature history into compositional and physical models. But we don't yet have a full answer that explains everything we see. As the only other example of an Earth-like planet with a magnetic field, Mercury's outcome is quite different. That today we have a axially symmetric but equatorially strongly asymmetric magnetic field, not like anything we think the Earth experienced in its 4.5 billion year history, meaning that the specific physical model that produces Mercury's magnetic field, and the presumption is that it's a dynamo like the one we invoke on Earth, involving motions in the fluid metallic core, has a different geometry or different boundary conditions that we still haven't discovered, but leads to a magnetic field that is offset more than any other planetary body, and not so Earth-like as we thought, but expanding the range of possible outcomes of magnetic fields in Earth-like worlds. And finally, we have the exploration of the polar deposits, the confirmation from a variety of experiments that water ice is indeed the most abundant material in the polar deposits discovered by radar astronomers in the 1990s, but the extra discovery from MESSENGER that there are volatile dark materials as well that are stable to higher temperature than water ice, that coat the water ice in most of the deposits and are postulated to be organic compounds like the water ice delivered from the outer solar system by comets and volatile-rich asteroids, leaving us with the interesting and seemingly paradoxical result that the planet closest to the sun that has the highest range in diurnal temperatures, 600 degrees centigrade on the equator, might have the best record of the process of delivery of ices and organic compounds from the outer solar system to the inner solar system, residing in these deep freezes at high latitudes in the permanently shadowed craters of Mercury. And of course, we invoke this process of delivery of organic material and water from the outer solar system to the inner solar system as part of our life origin story for Earth. We invoke those processes to account for ending up with an Earth-like body that has oceans and that has the building blocks of organic chemistry that at some point led to the origin of life. So we may have a witness plate to at least the later stages of that process, not on Earth, but on an object we didn't expect, the planet closest to the sun. So I'll stop there and take some questions. Thank you.